All right, then good afternoon, ladies and gentlemen. My name is Patrick Brandl, and it's my pleasure to welcome you and chair the first of the UKCCSRC virtual poster conference without actually presenting the posters. Each presenter will have 5 minutes to introduce us to the work, and this is then followed by a 10-minute Q&A. And this session, we will hear from the following three presenters. We've got Louise Hamdy from Swansea University. Apologies, Dr. Louise Hamdy, the only doctor actually in this call. And she will present her work on cross-linking polyamine sorbents, so solids for CO2 capture. Then she's followed by Abdul'Aziz Aliyu, and he will be presenting his research on selective exhaust gas recirculation and oxidative degradation at the packed facilities, as well as his GCCS modeling. And last but not least, we will have Paul Willson from PMW Technology, and he will be presenting their advances in the cryogenic moving bed technology. So first off, we've got Dr. Louise Hamdy from Swansea University. Louise is a research officer at the Energy Safety Research Institute at the Swansea University. Her main interests are in the design, synthesis, characterization of new polyamine-based carbon dioxide absorbent materials. She will be talking about cross-linking polyamines to design new adsorbents to target the ambient temperature absorption from CO2 from dilute streams. So Louise, if you want to share your screen, and then the stage is yours.
Hey, thank you very much for the introduction. Can you see my screen?
Yes, we can.
Is that full view?
You just need to swap the presenter view.
Right, okay. Sorry. Swap that, this one? Damn it. Let's just go with this then.
You can just go on display settings in the middle. So just go onto top. No, is this on the top of your screen? In the middle, display settings to your left of your mouse. And then you can swap the presenter and show coach view.
Here?
One to the left, and then you should have the single screen presentation. I can't see your mouse at the moment, so it's hard to tell. No, just go into the presentation mode, and then I'll take you from there.
Okay. Yeah. Okay. Sorry, I've got. You've got. How's that? Sorry, how's this?
So at the moment, I just see you open PowerPoint. Now we're on the presentation, perfect.
Fantastic. And what if I do this? Full presentation?
We still see the full presentation, yes.
Okay, sorry, I was using two screens, never mind. Thank you very much, Patrick, for the introduction. So I'm going to be presenting some work that my project students carried out last year and that we've been progressing with in the past few months. So our research group is focused on cross-linking polyamines to make solid CO2 adsorbents. Our previous research on epoxy cross-linked polyethyleneamine has resulted in very highly efficient and absorbent carbon dioxide materials, and they've been highly selective and have good multi-cycle durability. However, due to their low surface areas and their impenetrable mass bulk, they have actually had diffusion limitations at lower temperatures. So although efficient above 90 degrees, they are not ideal for direct air capture. And of course, we're targeting low temperature adsorption, looking towards developing these materials for direct air capture. So we are looking now at using a new cross-linker. This is a novel cross-linker to see if we can optimize these materials by balancing the cross-linking density with reactive amine availability to target the low temperature adsorption. So we're using this triazine alkyl bromide crosslinker to cross-link the polyethylene amine into a new material. We are using these starting materials in different ratios, 1:1 up to 25:1 amines, so amine to alkyl bromide. And this results in the product having a different amine to alkyl bromide cross-linking ratio. So we prepare these materials in slightly different ways. One set have been prepared in a vial at high temperatures and another under reflux conditions. This is V and R. So we've tested these materials at 30 degrees, 60 degrees and 90 degrees on TGA in 90% carbon dioxide and argon. The maximum CO2 adsorption is consistently higher for the lesser cross-linked adsorbents, is 10:1 and 25:1. And that's because these materials have a higher ratio of amine to cross-linker. The CO2 capacities for all of them are higher at the lower temperatures. All of the adsorbents have their lowest adsorption capacity at 90 degrees. CO2 uptake over the 2-hour adsorption period is highest at 60 degrees for the 10:1 V and 25:1. However, we can see that for 1:1, 3:1, 5:1, and 10:1 R, they reach their highest adsorption at 30 degrees, which is good for direct air capture. 10:1 R reaches a very good capacity of 2.31 millimoles per gram at 30 degrees. So this is a very promising material. So how can we rationalize these adsorption behaviors? We look at the SEM images, and the SEM of 25:1 V shows the materials composed of irregular globular morphology of fused particles forming larger mass particles. I want to point out this bar is 3 microns in size. 1:1 V is formed of discrete spherical particles up to 1 micron in diameter. 10:1 R is formed of discrete spherical particles of up to 3 microns in diameter. So adsorption is controlled by thermodynamics and diffusion. The 25:1 V experiences a diffusion barrier at 30 degrees. And that's why on increasing the temperature to 60 degrees, it's able to access higher adsorption. At 30 degrees, there is not enough energy there's not enough temperature in this, not enough energy in the system in order for that CO2 to diffuse into this fused particulate matter and access the amines. We see there's a lower diffusion barrier for 1:1 V and 10:1 R because these materials are formed with discrete particles. CO2 is able to access the amines in the interparticle space. So we wanted to then further challenge 10:1 R and see how its adsorption would be in dilute conditions. We can access low temperature. Can we access dilute condition CO2 uptake? In 10% carbon dioxide and nitrogen, maximum absorption was 1.5 millimoles per gram. And this was over a 3-hour adsorption period. Absorption at 60 degrees, we see again, is much faster and is equal to 30 degrees after the 2 hours at 1.4 millimoles per gram. So 1.5 millimoles per gram is about 7%, so this is good. However, in 400 parts per million CO2 and nitrogen, adsorption is very poor. At 30 degrees, we're only obtaining up to 0.2 millimoles per gram. So this is something we want to look at further and try and further optimize this structure so we can better access the low temperature adsorption by increasing our accessibility to these reactive amines. Further work will be focusing on breakthrough adsorption measurements in 10% CO2 in humid conditions to further test this material. So thank you very much for your attention.
Thank you very much, Louise. Now, the floor is open for questions. If you don't have an active mic, you can write your questions in the chat box, and then I will ask them to Louise. And I want to actually ask the first question. So I'm very interested in how the stability of those materials is. Have you done any degradation experiments, or what is looking like?
Yeah, we have actually. The materials are stable up to about 200 degrees, and then they begin to decompose once you reach about 250. They're well into decomposition state. But we activate them, as in we heat them up and remove the adsorbed species water or CO2 before the adsorption experiments at 120 degrees. Yeah, but they're thermally stable at post-combustion CO2 capture conditions.
Thank you very much.
Can I have another question, Louise? Thank you for your presentation. Yeah, you're right. You mentioned that. You mentioned that there are two different aspects affect on the CO2 absorption, from thermodynamics aspects and kinetics or diffusion. So if we consider the thermodynamic aspects, you know, because we had I think your amine group rely on the chemisorption. Is that right? So
Yes.
do you think that the regeneration energy is quite high when we have the amine group?
Yes. It's of course we want to aim to get that down. After each adsorption, we desorb at about 110 degrees. So it's fairly high. However, we want to see is if the CO2 is able to adsorb mostly on the surface of these particles. It should be easier to remove rather than the CO2 diffused deeper into the material.
And what's this temperature for desorption or regeneration techniques?
110 degrees is the regeneration temperature that we use. Yeah.
Okay, so you consider that your material is half chemisorption and half physisorption.
At the moment, we have more evidence to show that it is the major adsorption mechanism is chemisorption.
Okay, and sorry, my second question about your porosity or morphology you just investigated is that the morphology effects on the CO2 absorption, and you said that the size of the pore structure by SEM, and I wonder to know is that you said that is that the separate size is more effective, or the micropores volume, which one is more effective to diffuse more CO2?
We saw that the 25:1 is made up of far larger particles, whereas the smaller particle size in this case seems to promote higher adsorption at lower temperatures. However, we also acknowledge that the material which was smaller particle size but also had high amine content was far more effective than the one with the smaller particle size. So it really is a balance between the amine availability, amine content, and particle size. However, it does seem, looking at the 25:1 material, that high amine content didn't directly translate into higher adsorption at lower temperatures. It needs both structure and the chemical composition.
Okay, thank you very much.
Thank you.
Sorry, I forgot to unmute my mic. So we've got two questions in the chat. The first one is about the originability, and I think you mentioned it 110 degrees Celsius, and the second one is about the heat that is required to regenerate the solvent.
I'm interpreting regeneration heat as the regenerability. Oh, no, sorry, right, okay. The regeneration heat, yes, of course, is 110 degrees. the regenerability, we haven't carried out, I'm interpreting this rather as cycles, is that right? If so, we haven't carried out many cycles, adsorption, desorption cycles on these materials. However, the data that I showed at 30 degrees, 60 degrees and 90 degrees were all carried out on a continuous experiment of adsorbing, desorbing, adsorbing, desorbing, adsorbing, desorbing. So we can at least know that they're still effective at after 3 cycles.
Yeah.
But that is something that we would like to test further.
John Gibbons, can I ask a question?
Go ahead, John.
Yeah. So your criteria for performance are what? It's uptake in whatever it was, 120 minutes or something.
Yeah, we're looking at uptake over time in this case, yes. So that we can get an idea of the kinetics of reaction actually, and see how fast adsorption is.
And what do you think is important for air capture? Or, you know, for
I think for any
economic.
adsorption,
Sorry.
I would think that for any adsorption material, fast uptake is important. I mean, we can't leave. I think 3 hours a cycle is completely unrealistic. But
why do you think that?
Mostly because we've been focusing on post-combustion CO2 so far, and we understand that the absorption desorption cycles are measured in minutes, not hours.
So, but I thought you were talking about air capture then.
But yeah, looking towards air capture, I would just carry that through and think, for air capture, would we not need something that's effective? It has significant uptake in as low a time as possible.
It's not clear to me that you would. I mean, you know, if you're doing post-combustion capture, you've got a specific location and you've got a hell of a flow of flue gas. Things have got to happen. Whereas if you can just leave it lying around in a field, basically, it won't be so critical.
But then there's desorption as well. I mean, these materials have to be desorbed so they can be used.
Kinetics won't be a limit if you're heating it up. It'll come off quick, won't it?
Yeah.
So I think that's a different. I don't know. It's just not clear to me that you'd have the same constraints in those situations. I mean, apart from anything else in air capture, there's always a trade-off between putting in energy to move the air and just letting natural convection move the air to you.
Right. Just,
So
I'm afraid I have to cut you off at this moment, John, because we need to move on to the next presentation. But first,
tough chairs, yeah. Correct.
I'm sorry, John, but tough rules. But I just want to, Louise, thank you very much for your presentation. And also, there are 2 more questions in the chat. So if you might want to answer them, it's about what type of process would be best. Is it fixed bed? Is it fluidized bed? And the other one asks for how many gigajoules per ton of CO2 does the process require?
Thank you, I'll rest them.
So next up, we've got Abdul'Aziz Ali from Sheffield University. He actually graduated with a Master of Science in Energy and Environment from the University of Leeds and has currently submitted his thesis on post-combustion carbon capture at the University of Sheffield. He's passionate about environment issues and loves traveling around the world and photography. I'm afraid he can't travel at the moment a lot. However, he brought us not only 1, but 3 research works. He will be presenting his work on selective exhaust gas recirculation and oxidative degradation of MEA at the packed facilities in Sheffield, as well as the process modeling study using GCCS. And the stage is yours, Abdul.
Hi, everyone. Let me try to, well, before I start, I underestimated or overestimated the length of 5 minutes. So it's going to be very difficult for me to squeeze in all the 3 studies that I have done, because I really want to do justice to each and every study that I'm going to talk about. So I may not be able to cover everything. Let me try to share my screen right here. Okay.
We can see your screen now.
Okay, very well. So within the course of my PhD work, I have embarked on a number of studies. One of the studies that I'm going to talk about right here is selective exhaust gas recirculation and how that affects the performance of the CO2 capture process. Selective exhaust gas recirculation in series is basically a process where CO2 in the treated gas downstream of the CO2 capture process is being captured and recycled back to the gas turbine in order to boost the CO2 concentration in the exhaust gas. This process is expected to increase the CO2 capture efficiency in the absorber column and subsequently reduce the specific reboiler duty. The specific reboiler duty is basically the ratio of the solvent regeneration energy to the mass flow rate of the CO2 captured. What I have here on my screen, let's start with the y-axis to the right. This is the absorption capacity, and this is the CO2, the ratio of the CO2 capture rate to the mass flow rate of the solvent. I'm getting back to the y-axis. On the left, we have the change in energy consumption, and this is the change in the specific reboiler duty against the best case specific reboiler duty. On the x-axis, I have the CO2 concentration in the flue gas just before the absorber column. So as the CO2 concentration is increased from 5 volume percentage to 9.1 volume percentage, the absorption capacity, which is in the orange dotted line, increases from 5.0 volume percentage of CO2 to 6.6 volume percentage of CO2 before it declines. This result tells us that the absorption capacity is highest at 6.6 volume percentage of CO2. And unsurprisingly, this is the point where the specific reboiler duty is lowest, by 25% against the best case specific reboiler duty. I need to note that the 6.6 volume percentage that yields the least specific reboiler duty is plant specific to the packed facility, and other CO2 capture facility will have to run their own campaign in order to identify the CO2 concentration that yields the least specific reboiler duty. So what's the takeaway from this result? And that is, before 6.6 volume percentage of CO2, mind you, the CO2 capture efficiency is all capped at 90%. Therefore, before 6.6 volume percentage of CO2, the solvent flow rate is low to translate to any reasonable CO2 capture. And above 6.6 volume percentage, the solvent flow rate is high. That translates to lower residence time in the stripper and reboiler. Therefore, the stripping performance is very low. So in conclusion, even though selective exhaust gas recyclation in series has been put forward by researchers to decrease the specific volatility, which is true to some extent, my conclusion is that selective exhaust gas recyclation in series is not favorable for the following reasons. One, the operating and capital expenditure of nanomaterials for CO2 capture will have to be taken into consideration, that is responsible for recycling the CO2 in the treated gas back to the gas turbine. That's one. Secondly, with selective exhaust gas recyclation, the solvent flow rate increases. Therefore, your solvent inventory increases. Therefore, the cost of the solvent management and the cost of the solvent disposal increases. Third, with selective exhaust gas recyclation, the pH value of your solvent decreases. And under that circumstance, it's liable to increase the corrosion of the internal equipment of your plant. The corroded ion in your plant is liable to corrupt your solvent, which increases your operational expenditure, and also increases the capital expenditure due to the nature of the corrosion because of the lower pH value. So, so this is what I have to talk about this afternoon. Thank you for listening to me. I have more studies, but I do not want to exceed my 5 minutes, so pretty much.
Thank you very much. While everybody's thinking about the questions, I'm opening actually with a question myself. So EGR increases the CO2 composition. From my end, for my research, that's essentially all I need to know. But how does EGR, is it possible to retrofit on an existing plant, or do you have to design it, power plant, an NGCC power plant with EGR from the first place?
If I understood your question, if you're going to retrofit your carbon capture facility to your power plant, the CO2 capture system will have to be designed in line, rather together with the EGR facility.
All right, so you can't copy paste an existing, let's say, NGCC post-combustion capture unit and just throw it onto an NGCC with EGR.
If you could rephrase your question a little bit clearer, perhaps I may have a full understanding on exactly what you're trying to ask me, please.
So we have seen some feed studies designing a post-combustion, a solvent-based post-combustion unit for natural gas-fired power plants. Yeah. And the CO2 composition of those power plants is usually much lower, or the flue gas of those power plants is usually much lower than power plants using EGR. And it's not only the CO2 composition, my understanding is also that the flue gas flow rate will change between a power plant with and without EGR.
Yeah.
Now my question is, can you use a very similar design or even the same plant, the same CO2 capture plant for both power types?
If you are designing your CO2 capture facility with EGR, evidently the capacity of your CO2 capture facility will have to decrease because of the reduced flue gas flow rate into the CO2 capture facility.
All right, thank you very much.
Thank you as well.
Again, a short reminder, if you don't have an open mic, you can write your question in the chat and then I will ask them.
Can I ask a question?
Yes, please.
So EGR increases the composition of like carbon monoxide and unburnt hydrocarbons coming from the gas turbine. How do they affect the capture plant?
My research gravitates towards flue gas from gas turbine combustion, which unlike coal-powered power plants, does not have the issues of NOx, to be honest.
Well, I'm talking more about like carbon monoxide and unburnt hydrocarbons. Do they increase when you have EGR?
When you are recycling part of the flue gas back to the gas turbine, evidently you are increasing the carbon content into the gas turbine. In my understanding, the CO content will be decreased with EGR going into the CO2 capture facility, simply because the flue gas that's being introduced through the CO2 capture plant will be reduced by, for example, if I reduce the flue gas going into the CO2 capture facility by 50%, that means I have effectively reduced the CO content and the issues that will arise from this concentration by 50%.
Okay, thank you.
Thank you.
All right, Dan, thank you very much, Abdulaziz, for your presentation.
Thank you.
And then we're going over to the last presenter, but not least. So I think, Abdul, you're still sharing your screen, so if you can end sharing it, then Paul can already set up.
Where can I go to? The red button to the top left?
Let's see if I can stop it.
Oh, stop share, I can see that. Fantastic.
Perfect.
Yeah.
All right, so next up we've got Paul Willson. Paul leads the process development company PMW Technologies, and he has been working on the moving packed bed cryogenic capture technology since 2016 and was involved in the very first carbon capture competition for, back in the day, DEC. Paul's background is in power generation, and unusually he's qualified as an electrical engineer. His poster will introduce us to the fundamental basis and the recent advances of their cryogenic technology. So with that, Paul, the stage is yours.
Thank you very much. Good afternoon, everybody. Let's see if I can get my screen, the right screen here. Okay. Here we go. Right, I'll put the poster up. As you have said, I have been working on this technology with our colleagues at the University of Chester since 2016. We did a major feasibility study also with the University of Sheffield and a couple of industrial partners in 2017-18, which was reported at the Greenhouse Gas Conference in 2018. Since then, quite a lot has happened, and I was setting out on this poster where we got to. The process outline on the left here shows quite crudely what our process is about. At heart, there is in the separator stage a circulating bed of chilled metal beads that are used to freeze the carbon dioxide out of a pre-cooled gas mixture. The use of a metal bead as an heat exchange and mass exchange intermediate avoids problems of frost buildup, and we maintain a very high heat transfer within the desublimer section where we frost the gases. The frosted bed is taken out of the contact region and into the sublimer where we warm it, and we reach temperature about -80, only about 20 degrees warmer than the desublimer conditions, to recover the carbon dioxide as a gas. Our refrigeration system provides cold at the top in the bed cooler and rejects a large part of its heat in the sublimer to recover the carbon dioxide. Since it works through a small temperature difference, it has a relatively low energy consumption. The temperature difference between the gas leaving the separation and arriving drives a separate cooler drier stage, which is a similar packed bed circulation that takes moisture, frosts out the moisture in the incoming gases using the cold from the lean gases. In the last couple of years, we've done a series of projects published in various papers internationally. So the first one, which Carolina Font Palmer undertook the work on with us, is on biogas, where biogas typically contains 30 to 50% carbon dioxide alongside methane, but also contaminants such as hydrogen sulfide, benzene, and siloxanes. If you're going to upgrade biogas to inject it into the gas grid, those contaminants have to be eliminated. So using our Aspen Plus modeling, we estimated the impact on the contaminants of the process. What we found was that the volatile contaminants were all condensed out in the cooling stage before it reached carbon dioxide separation. You can see here dramatic reductions in concentrations of the various contaminants. Hydrogen sulfide is the only thing that survives the process, and that just has to be cleaned up chemically either before or after the carbon dioxide removal. But this means you have a simpler process overall for upgrading your your biogas, and the energy consumption is considerably lower than the competing processes. The second application we looked at was in microgas turbine. Microgas turbine, as Abdul'Aziz has been testing, uses a small gas turbine. It has a very high dilution of the carbon dioxide in the exhaust gases. So the typical figures we've seen are 1.6% carbon dioxide in the exhaust from burning natural gas. The analysis we did looked at both burning biogas and burning natural gas in the gas turbine, working with the University of Chester and the University of Stavanger. Let's screen back. Excuse me. Right, there we go. We applied 90% carbon capture in each case, and we drew our control volume, thermodynamic control volume, around the whole system so that the parasitic energy consumption of either the amine process or the A3C process were accounted for properly. What we found was that the A3C process, which has parasitic electrical consumption, reduced the carbon intensity of generation quite significantly. MEA, which required additional fuel to be burned to meet the heat demand of the stripper column reboiler, generated only effectively a 50% improvement in the intensity of generation burning biogas. The situation was closer on the natural gas case, but here both the processes are running at an extreme with a residual content of carbon dioxide of 0.16%, only 4 times the level in the atmosphere. The third application we are working on at the moment is an application to shipping. I show a picture there of one of the case studies we're working on. We're looking at two case studies, a car carrier, 10,000 ton, and this Victoria of Wight, the ferry going to the Isle of Wight. The intent here is to understand how the cost of abatement is changed by using a carbon capture process rather than using a zero carbon fuel such as ammonia. What we've found so far is that the process is indeed feasible. The equipment isn't unreasonable size or weight. The storage vessels we require for carbon dioxide are relatively modest. It's to do with the relatively small energy consumption of ships compared with their cargo size. We've used Aspen Plus performance modeling. We've then done cost estimation based on the capital cost of equipment, reference fuel costs from BEI's forecast for the future, and on a consistent basis with work done for the Department for Transport, we've calculated our cost of capture at around £50 a tonne for the different cases. And at the scale of less than 30,000 tonnes a year, that's quite a good cost. Amine can't really go there. We obviously, in order to make the comparison fair, have had to look at the costs of unloading and storage of carbon dioxide before transfer into the clusters. And the transfer cost is of the order of 10 to 15 pounds. And then you obviously incur the cost of transport and storage to offshore geological store. The overall cost is around £100 a tonne for using consistent assumptions with the comparison for the zero carbon fuels for 2031, which would be £180 a tonne. So this is a significant thing in terms of the result. And we have actually already, despite not having published this, we've already generated quite a lot of interest in the application. In the background to all this work that we've done, we've made significant technology and cost advantages, as you can see in the bottom right here. These include process improvements, but particularly better integration and better design of our refrigeration system. This now includes a multi-component refrigerant with low greenhouse gas potential. The graphic illustrates the improvements we've made since the 2018 report. Particularly notable is the improvement in processing low carbon dioxide content gas from a gas turbine, 3.5% mole. We've got the energy consumption down to 279 kilowatt hours per tonne, almost exactly 1 gigajoule per tonne. And for the biogas case on the right, we're now down to just about half gigajoule per tonne for removal of carbon dioxide. This isn't the end of the line. We're still seeing improvements. It's not easy with the kind of multiple cycles of gas to clean, bed, 2 cycles of bed, and the refrigeration cycle to optimize all of these simultaneously. And we're hoping that exergy analysis, for example, will help point to the right direction for further development. We certainly don't see this at the end of the line yet. Thank you.
Thank you very much, Paul. While everyone else is thinking about the questions, I've got actually 3 questions, and I think that should be rather quick fire for you. When you say you've got a mixed component refrigerant cycle, I assume it's a mixed Joule-Thomson refrigerant cycle?
It's a conventional evaporation cycle, compression, condensation, evaporation, refrigeration cycle. It's unusual in the way that it rejects heat, but that's the only thing that's unusual about it otherwise.
All right. And then I think what strikes me about this process that although it might be very low on operating expenditure, I assume it to be very highly capital expensive. with all the, let's say, cold bogs, all the heat integration, heat exchangers, and so on that you mentioned that maybe drove the cost reduction earlier?
It's certainly the heat exchangers are more costly, but heat exchangers are relatively inexpensive as pieces of process equipment. And our analysis certainly doesn't show the process to be alarmingly capital intense. It has costs associated with compression, of course, but these are not outstanding. It's overall levelized cost of the shipping application of £50 a tonne takes account of both capital and operating costs, discounted over 20-year life at 10% discount rate. So it's a fair number.
Thank you very much, Paul. The floor is open for questions.
Can I ask, Paul? That was really interesting. That's a new thing for me. Seeing this cryogenic capture, and I was wondering regarding the ship. They obviously produce a lot more pollution than just CO2. I know you did take into consideration other pollutants in one of your other studies, but can you describe how this was accounted for in this study? Other heavy pollutants from ships?
Certainly. An important part of the interface between the ship and our process is the cooling and cleaning of the exhaust gases. The two cases we've looked at are burning LNG, which is a very clean fuel, and burning MGO, which is marine gas oil, and that has quite low sulfur contents now. It's been forced down. The engines still produce NOx, and both of those components need to be taken out before being shown to our process. What we find is that the engines themselves and the post-treatment of the gases to comply with environmental requirements now include things like SCR that mean that the NOx levels are extremely low. The sulfur levels that remain are modest, and when we cool the gases, we reach the point where both the water and the sulfur content come out as liquids and are simply removed from the gases. The concentration of sulfur is not so high that it knocks holes out of every metal. It certainly needs to have some care and materials choice in that section of the heat exchange.
Okay, thank you very much.
We've got, we had a very similar question in the chat about the sulfur emissions. So what are you doing with the remaining SOx that have been separated?
Right, the SOx comes out as part of the condensate, and that's neutralized and discharged to sea as part of effectively the scrubbing of the incoming gases. That's part of the total cleanup process. So we end up with, I guess, sodium sulfate going to sea.
All right, and if there are no other questions left, then thank you very much, Paul.
Thank you.
And then thanks to all the presenters, Louise, Abdulaziz, and Paul again for the first session. And now we have a short 10-minute break, and then we'll hand over. Louise will be chairing the next session, and I think we've got a range of other presentations following it. Thank you very much.
Okay, so I'm going to hand over to Louise, who's chairing the next half of our poster session for us. Thank you, Louise.
Hi, Carrie, thanks for that. 2 seconds. I just want to make sure the speakers are available. Is Mathew there? Do we have Mathew?
Yeah, I'm here.
Oh, we do. Okay, perfect. Okay, welcome back, everyone, and welcome to the next part of our poster presentations. Our next speaker is Mathew Wilkes. Mathew is a third-year engineering doctorate student from the University of Sheffield within the UKCCSRC Centre for Doctoral Training in Carbon Capture and Storage and Cleaner Fossil Energy. Mathew will discuss the transient operation of amine-based CO2 capture for quick response open cycle gas turbines. So it's over to you, Mathew.
Okay. Can everybody see that?
Yeah.
Okay, awesome. So today I'm presenting findings from a computational study into the transient operation of post-combustion CO2 capture systems. So transitioning to a low-carbon electricity grid requires technologies to work in partnership with renewable power generation to ensure security of supply. So open cycle gas turbines are capable of this as they have quick startup times and operational flexibility. So coupling OCGTs with post-combustion capture of CO2 can aid in decarbonising the power industry. And this study looks at developing and validating a dynamic PCC model and analysing the flexible operation of OCGTs, then bringing these two together to look at the transient operation of PCC attached to a small-scale OCGT plant. A dynamic rate-based CO2 absorption model using the benchmark 38% monoethyl amine was developed in GPROM's GCCS. Due to time constraints, I won't go into detail about the model. But it was validated against steady state and dynamic pilot data from Tate et al. 2016, who presented flexible response scenarios for gas-based post-combustion capture. Only the steady state validation is shown here due to space constraints with the poster. But the model proved to accurately predict the key performance indicators of the process, with the capture rate only 0.04% out. The next stage was to look at OCGT operation, and I did this using the balancing mechanism reporting service, which provides data on the generation and demand within Great Britain. I transformed the data into heat maps specific for the month of January, which is the busiest month. OCGTs typically come on the system in the winter months between December to February and are used for peak demands in the evening. I don't know if everyone can see my mouse, but it's this part here, so it's typically coming on in the evenings. This sort of information you can find out in the literature really easy. What's interesting about this data is that it shows the transient behavior as well. So if you look here, you can see that it jumps to different power outputs within the same operating cycle. And it can go to multiple operating cycles within a 24-hour period. And analysing the data over the previous 4 years showed that the average operating cycle is around 5 hours. So I translated this into flue gas flow rate changes. So I scaled up the model to handle flow rate from a 10.4 megawatt Siemens SGT 400 gas turbine. And I used the startup, shutdown and ramping times that Siemens provided. And then looked at 4 different dynamic operating scenarios. So there was a base load where there was constant 5-hour operation. And then the subsequent 3 scenarios looked at changing flue gas, the flue gas and solvent, and then the flue gas solvent and reboiler steam flow rates. And then on figure 2 over here, you can see the CO2 capture rate over the course of the operation. And the first glaring point is that the CO2 capture rate decreases over the entirety of the operation. And that is because the model includes the startup procedure. The startup procedure. So the plant needs time for the loadings to stabilize and reach a steady state. And in the operation, the flue gas flow rate drops to 70% and then 50%, as can be shown with the step changes in capture rate. And when controlling the solvent flow rate to maintain the liquid to gas ratio, there is an increase in time average CO2 capture rate. And then when you ramp the reboiler steam flow rate in accordance with the flue gas flow rate, you then get a small saving in, or you get a lower reboiler duty, albeit a very small decrease, but a saving nonetheless. So this shows that in very highly transient systems, the frequent changes never allow the system to return to steady state, and it actually benefits from this in terms of capture rate and lower energy demands. But it is worth noting that this transient operation had an effect on the quality of the CO2 produced, and further research is required on the effects of transient operation on the desorption unit and the downstream CO2 compression system. Thank you very much for listening, and I'll be happy to answer any questions.
Thank you very much for that, Mathew. Now, would anyone like to ask any questions? Okay, Mathew, I was wondering, can these, how easily is it to adapt a power station for these open cycle gas turbines, or do they already exist?
So they're just a simple gas turbine configuration.
Okay.
So they have the lowest capex of natural gas turbines, because all it is a combustor and a turbine. There's no steam generators involved.
So it's a simplification? It's
just the very simple version. So there are a few operational in the UK units. No.
Okay. You mentioned, sorry, let's go to another question. Would anyone else like to ask a question?
Yeah, so where does the steam come from to regenerate the solvent?
So that's either from an external power source. There was one thing that I looked at, or that I want to look at, is if we can incorporate the waste heat from the gas turbine. So I know with like combined cycle gas turbines, some of the steam generator is redirected, so that the redirected to the capture plant, hence why you have an energy penalty with these sorts of systems, and you have a lower power output from the overall plant. One thing I want to look at is, can you do that with an open cycle gas turbine? As they have no steam generators, you could then effectively have the same power output and have no energy demand for the capture system.
So, and how are you getting the flue gas to the right temperature to go into the absorber?
So I think the input used from the Tate model was around 40 degrees. And I just used that as an input. So just...
Sorry, I didn't catch that. What was the temperature going? I mean, the temperature's what coming out of the gas turbine, 400 C or something like that?
Higher than that. I think for the Siemens ones I was looking at, it was around above 500 degrees. So there was,
how did you get the temperature down to something that wouldn't, destroy the absorber?
That's a good point. That's something that I've not looked into, because I've just scaled it so that it could, I've scaled it from those pilot tests, the pilot testing at Chemtech. And I think the next part of the project is looking at how I can incorporate some sort of heat transfer so that there's no energy penalty, and that it can get down to the 40 degrees necessary for the input.
How long have you been working on this?
2 years for this, but I'm also looking at CO2 adsorption as well, and CO2 compression.
So how long have you got to go? I guess a little while.
Oh, I've got a year and a half.
Okay.
Okay, Mathew, you were talking earlier about the lower CO2 quality from captured CO2. Can you expand on that a little bit more? What do you mean by lower quality? Do you mean impure?
There was a slight drop in purity, so there was a 1% decrease in the compression leading towards the compression system, and the regeneration in the desorption unit went down by 6%, and that was when that AOC, when the reboiler steam flow rate was also changed. So I just want to look into that a bit more and see how we can minimize that sort of fluctuation going towards the CO2 compression train, which has problems with surge control. So I want to make that as stable as possible.
Okay, thank you.
Sorry, is
Yeah.
that absorption stable at 400 degrees?
No, it wouldn't be operating at 400 degrees. It needs to be brought down to just over 40 degrees.
Okay, and what was the flow rate, flow ratio between liquid to gas?
Let me just get it up. It was 2.86 litres of liquid per metre cubed of gas.
Okay, thank you.
Would you like to address Phoebe's question about in the chat? Are you working with adsorption?
Yeah, so
also?
I'm currently developing and validating an adsorption system to be worked with this 10.4 megawatt gas turbine. And then I'm going to do an economic comparison between them to see what the benefits would be, or which one is more cost effective in a transient manner.
Okay. Thank you very much. Are there any other questions?
For the adsorption system that I'm looking at, is that?
Yes.
ZLX, I think I'm currently using.
Oh, you're explaining which material you're using.
Yeah, Zeolite 13X, as this is the one most commonly used for mathematical models within the literature. So to enable a comparison to other sources, I think that's the fairest option.
Sorry, and does it affect on the, because you have it steamed, so does it affect on the affinity of water, a vapor during the process if you use the zeolite?
Yes, so in the adsorption system, I have to have some sort of dehydration unit to remove the moisture,
Okay.
because that's one of the main issues with zeolites.
Yes, thank you.
Ian, would you like to ask a question? Would you like to take that, or would you like? Were you having a problem asking a question? We can't hear you, Ian. And there we go.
Hello, I've just been unmuted. Yes,
Sorry.
no, I don't want to ask a question now, but I had put a note on referring to Friday when I wanted to ask a question. Now I couldn't attract attention to get my question, get the opportunity to do so, but I don't really want to divert the meeting into that now.
I know, of course. Also, everybody feel free to put your videos on. We're mostly looking at presentations at the moment, of course, anyway, but do feel free to put your cameras on. Next, we're going to our second speaker. So Patrick Brandl is our second speaker. Patrick's a final year PhD student in chemical engineering at Imperial College London, specialising in molecular thermodynamics and process engineering in the net zero context. His research focuses on screening and designing cost-effective CO2 capture solvents. Patrick will discuss the costs of increasing the capture rate of solvent-based post-combustion systems towards net zero emissions. Over to you, Patrick.
Right,
Okay.
someone just unmuted me and unmuted me. Can you hear me now?
Yes, we can. I don't know why we're...
Lovely. Can you also see my slides?
I can.
Yes, we can.
Brilliant.
Yeah.
Then I'll jump right into this. So what you see here is a typical CO2 flue gas source with a specific composition of the CO2 in the flue gas, followed by a post-combustion capture facility utilizing solvents. And a common convention is that you capture 90% of all incoming CO2. So if you have a flue gas stream with 10 molecules of CO2, that means you sequester 9 of those molecules and 1 of them is still being emitted. And all the emissions still going into the atmosphere, that's what we refer to as residual emissions. And in a net zero world, those residual emissions should be 0. So one way to do it is you increase the capture rate close to 100%. The problem is with solvents, that's not as easy done as with solids that we've been hearing about earlier. So the key question of my research was, how high and at what cost can you go with the capture rate until it is cheaper to offset the capture cost and the residual emissions rather by using negative emission technologies? Those technologies are, for example, bioenergy with CCS, simply planting trees, afforestation, or direct air capture. And the result looks like this. So if you start from a typical 90% capture rate and you increase the capture rate, then the cost profiles on the y-axis, you've got your cost, the dollars per ton of CO2 that you're paying, depends on the flue gas composition that you're looking at. To put some reference numbers into here, 4% more would be a gas-fired power plant, sort of 8% would be a gas-fired power plant with EGR we've been hearing about earlier, 12% more would be a coal-fired power plant, and everything higher would be an industrial facility like hydrogen, steel, iron, cement. And you can see that the cost profile is rather flat for rather concentrated streams up to 98% capture. If you have, however, a more dilute gas stream, then the profile is more strict and you have a higher cost increase. Now, what I'm saying is that you can offset with negative emissions. And the word offsetting, I understand, has a different meaning as well. Some people refer to it as indirect capture. I like the term mopping up residual emissions the most because that's what we're trying to do. So what I quantified is, depending on what flue gas composition you got, you go up to a maximum capture rate, and as soon as you hit the limit where your negative emission technologies are cheaper than increasing the capture rate at your flue gas source, then you should not capture this additional ton, but rather use negative emissions. The second point that I looked into is how can you actually try to finance this? And it's a rather complicated chart, but in a nutshell, the color is your cost of capital. So your capital recovery factor, a normal one would be between 10 and 11%. Very cheap access to capital would be 2. So if you're a national bank gives you a cheap loan, and very expensive cost of capital would be 22%. And the takeaway is that even if you have very low CRFs, you will not get there to drive CCS out. What we found to be more effective is a combination between investment credits, such as Section 48A in the US, which gives you a percentage of your capital investment back, and our Section 45Q tax credit, which gives you, if you store CO2, $50 per ton of CO2. And we found this to be more effective to breach or break even than simply reducing the CRF. So what I want you to take away from this is that the famous 90% number, it's a convention, but it does not represent a hard limit. Yes, it's possible to go up higher than 90%, up to 98%. However, at some point you have to mop up residual emissions with some negative emission technologies. And it is more effective to balance a tax credit style and investment credit style incentive rather than just providing cheap access to capital. And with that, I'm happy to answer your questions.
Thank you very much, Patrick. Would anybody like to ask a question?
Yes, Patrick. What ambient conditions was it?
So the CO2 capture plant that I'm modeling is utilizing a 38% aqueous MEA. It's a fully rate-based modeling.
Conditions. What was the temperature?
Oh, right. So the absorber is modeled at 40 degrees Celsius, and the CO2 flue gas that comes in is preset. So I've got a direct contact cooler, so all the flue gas will be cooled down. And depending on your flue gas composition, that temperature changes. So I took some reference cases from NGCC power plants to coal-fired power plants to hydrogen plants and so on.
I think it depends on what you can reject heat at from the system, you know?
Oh yeah, you simply have to redesign the DCC in front
I guess
of it,
what I'm saying is, I think it's a lot easier to get high capture levels on a cold day than a hot day.
Well, this depends obviously on your capture technology as such, but for this analysis, the ambient condition was fixed, constant. So you do not see a different ambient condition between the cases here. But I agree with your statement in general.
And then the other thing is as well, I guess, what electricity price you're getting, because basically your capture is just lost electricity, and sometimes electricity price is negative.
Yes, I fully agree with that. But the problem is that if you try to, hold on, let me quickly jump to the other slide. If you try to model a system that covers a range of those flue gas compositions, there is no power plant emitting 30 more % CO2. So you have to detach from a mother power plant. So what I said, it's a CO2 flue gas source. That CO2 flue gas source could be an industrial facility producing a product, and that is not electricity. That's why I'm reporting the capture cost per ton of CO2 and not per megawatt hour. I understand that.
You should say that though. Yeah, anyway, the best place to get the heat from an industrial source, if you don't have waste heat available, is a CHP unit. So you effectively lose electricity again.
Yes, and I've got a standalone source to produce the steam to regenerate the solvent in those cases. Yes.
But I think, you know, you would use combined heat and power, so you'd be generating electricity from that source, really. If you just burn gas, it's a thermodynamic crime.
Well, yes, I agree, and I understand where you're going. However, this does not impact the point of how much you capture.
But anyway.
Are there any other questions? No. Patrick, I was wondering what are the ultimate costs we're looking at if we're to start capturing CO2 in this country? Like, I'm trying to get my head around our utility bills.
If I knew only that answer, what I can tell you is the cost that we're looking at here excludes transport and storage, and okay. A widely distributed number is $20 per ton of CO2 for transport and storage. The large-scale projects that are out there in the world that capture CO2 from either a hydrogen plant or a power plant are around $40 to $60 per ton of CO2. So I would see a cost decrease getting down to maybe $20, $30 per ton of CO2, and there's also the long-term target for solvent-based technologies at least. However, this famous $20 per ton of CO2 is rather difficult to actually achieve because so far no one has proven it, yet many studies that simulate something end up at the $20 per ton of CO2 cost number.
And you were saying that that doesn't include transport and storage, but of course, the less pure the CO2, the more expensive it will be to store. I understand.
So yeah, I agree with that. However, what I do is I change the operating conditions of the capture plant such that the CO2-rich stream that goes into your transport and storage network always reaches the minimum quality In my case, that is 95% CO2 and the rest is water. And then you go into the dehumidifier and compression stages.
Thank you. I've got one message here. Hassan, would you like to ask your question? Or okay, Hassan's asking, which solvent do you use for capturing? Is it a physical or a chemical solvent?
So I'm using a chemical solvent, which is the literature benchmark of 38% MEA. However, my model is able to replicate any solvent, really.
Okay. Any more questions? Okay, thank you very much, Patrick.
Thank you very much.
Thank you. We'll move on to our next speaker, who is, well, we're ready, Phebe Linette Bonilla Prado. Phoebe's an environmental engineer from Mexico who's currently in the 3rd year of her PhD at the University of Sheffield, looking at alternative carbon capture technologies. Phoebe will discuss molecular simulation as a powerful tool to better understand the interaction between CO2 and the absorbent material hydrotalcites. So over to you, Phoebe.
Hello, everybody. Thank you very much for attending. And well, I think this is a little bit out of the realm of process simulation, which has been the main issue here. However, I hope you find it interesting. And well, I just want to share with you, I was thinking about doing the poster, so I've never shared things. Can you see the poster now?
Yeah, we can.
Great. Okay, so let's see. First, well, as you have mentioned now, I'm looking at molecular simulation using hydrotalcite. And well, first I'm looking at solid absorbents, hence I've been asking about solid absorbents in the whole sessions. So what I really want to know is if they're a better option than the typical MEA, because, well, preliminary studies have suggested that they have, well, they require less energy to do the regeneration, which could be a good advantage over the usual chemical solvents. Another thing that we're looking at is from the perspective of the process simulation, you cannot always say how the material is behaving when the CO2 molecules come, and having these insights can help us to see if we can tweak a little bit the material so we can improve its performance, and that's why we ended up doing some molecular simulation. So first, just a little bit about the absorbents. As I mentioned, they usually have a lower requirement for regeneration, and also they have a wide temperature and pressure range of applications. So you can use them for pre-combustion or for post-combustion. In the case of hydrotalcite, you can use it for both, which is quite nice. They can be used at very high temperatures. So it's kind of a good material to do these type of studies. Another thing is that they comply with these characteristics of the absorbents that we want. So it has a high surface area, large porosity if it's activated. What I mean is it has to be calcined. You have to heat up the adsorbent about 400 degrees Celsius, which has been like the optimum temperature found by other studies. However, well, as I'm going to tell you later, that depends also on how did you produce that hydrotalcite and what elements are in it. So another thing is they present fast kinetics. They're highly selective on the CO2. The stability of an absorbent is quite important to do all these regeneration cycles studies. However, most of the research found has looked just only at the absorption capacity at the first cycle, you could say, and at very small scale. So it's actually very hard to know how it will behave at a larger scale. And there's a bit of discussion regarding if it's thermally stable, because some studies have found it is, some others say say against it. And well, it depends again on how you created the hydrotalcite. And again, well, it's easy to find or easy to synthesize, better said. And in comparison with some of the chemical solvents, they do not need a special disposal because, well, they're not corrosive, they're just a clay, and well, they're quite benign, you could say. So coming to the material again, I'm looking at an anionic clay, which means that here we have a layered structure. It is also called layered double hydroxide. And so the hydrotalcite, it has a base of cationic layers with hydroxyls. And then you have an anionic layer in which you can have different elements or molecules. And this repeats like infinitely if you want to look at it like that. And the main problem with the study so far has been that there are so many different elements you can put in here for the cations and the anions that it's hard to do like an experimental setup with all of them. And that's another thing what we are pursuing with the molecular simulation, to be able to do all this screening without actually carrying out all the experiments, which wouldn't be very practical. So, and disadvantage of this material is that in contrast with chemical solvents, you could say it has a low absorption capacity. So hydrotalcite has been between 0.1 and 1.7 mole of CO2 per kilogram of hydrotalcite. However, this can be improved depending on the conditions you put it to work and how you synthesize it. So yeah, I mean, what I think the takeaway message of this is like hydrotalcite has many ways of existing, but we're looking at the one that has proven to be the best for CO2 capture so far. So we have been trying to study the cationic layer with magnesium and aluminium and the anionic layer with the carbonates. So for the molecular simulation part, first, there was no, in molecular simulation, you're looking at physics in a different way. So Newtonian laws kind of break, and you have to look at quantum physics if you want to be very, very specific. However, it takes a lot of computational power to look at more complicated systems. And in the case of the hydrotalcite, well, this is quite complex. So we cannot dream about doing that with quantum physics, and we then rely on on force field methodologies, which do use the Newtonian laws, but they take into account the parameters found from the quantum physics. So what we did first was to develop a force field, which is a set of these parameters that tells the program how the atoms behave with each other. And then we run the simulations. So first we did some molecular dynamics simulations. We created a force field, we did the simulations of how we heat up this material, and then we can go and do the Monte Carlo simulations about the adsorption capacity. So, as I mentioned, we have to heat up the hydrotalcite about 400 degrees so that it is activated and it can capture CO2. And so we did that in the simulation. And in order to validate that, we try to compare the surface area of our calcined material against the experimental data that we have, and it's actually in the range that we expected, like in the upper range. So these two blue dotted lines are the range of information I found of the surface area of the calcined hydrotalcite, and we can see that ours, as the temperature goes up, then the surface area goes up, but then when it cools down again to room temperature, you could say, then the surface area is activated, so it has a higher one than the previous when it was fresh. So we were quite excited about it. However, it has a lot of details regarding the force field because it's quite hard to get the right number to simulate an accurate simulation, well, an accurate calcination, you could say. However, we started doing the grand canonical simulations, and well, the numbers that we found for the adsorption capacity was completely off of the charts in contrast with experimental data, which is not what we were expecting. However, an interesting thing that we found is that the physisorption in all the cases that we were looking at remains about the same, and the chemical adsorption is the one that varies a lot depending on the chemical potential, which is the change in the energy depending on the pressure and the temperature that you can have when you add one molecule. So the takeaway message of this is that, okay, we are going in a good path regarding how the material can be calcined. And using that calcined structure, we can start looking at the adsorption capacity. And well, for the adsorption capacity, we still have to go through this chemical potential value in order to obtain the density first of the gas that we need, so that we can put a value that it's actually accurate or more similar to reality. So yeah, as conclusions, well, hydrotalcites look as a very promising material. Molecular simulation can help us to do a screening of the material once we have these parameters set up. And yeah, we're still working on it, and I will be very happy to take any questions.
Thank you very much, Phoebe. Would anybody like to ask Phoebe a question? And I was wondering, Phoebe, actually, you mentioned the low capacity of the hydrotalcite. Under what conditions are those values obtained? Conditions of concentration and temperature and
yeah, like how did you get that? Okay, so
water, all of that.
As I mentioned, there's a lot of research done on the adsorption capacity, but under various things. So one of the problem was the way you produce the material, and the other one is that most of the studies use TGAs, and they put either pure CO2 or they have an atmosphere of CO2 with argon with about 15% of carbon dioxide. And most of the studies look at lower temperatures, such as 30 to 60, but it has been seen that hydrotalcite can work at 200, which is kind of the temperature that we were aiming to, because we want to see if we could put the adsorption just after the post-combustion without cooling the gas as much. So yeah, that's why it's a very wide range of adsorption capacity.
Okay, so this is under all conditions, the absorption capacity is up to 1.7 moles.
Yeah, so that's for the pure hydrotalcite. There are other studies that, for example, use the hydrotalcite as the powder, and they put it on top of another base material. Mm-hmm. So you can have carbon nanotubes, or you can have maybe the hydrotalcite and put some carbonate of potassium on top, and then you achieve almost 10 mole of CO2 per kilogram. So it depends on what are your aims. So in our case, since we're looking at the molecular simulation, which is quite complex, only with this, like the simplest hydrotalcite, we rather focus on getting that well done first, and then we can think about maybe doing the supportive material, or changing the other elements that we can play around. So yeah, I guess that's what I wanted to say.
Okay. Thank you. Hassan, would you like to ask your question, or would I read it out? Hassan's saying, since the flue gas temperature is already high, 400 degrees, for better absorption, but how do you regenerate the adsorbent? Sorry, how do you regenerate the adsorber bed to increase adsorption capacity? Could you address that?
Yeah, so what I understand is that about what temperature I should do the regeneration of the adsorbent. Okay, so around 300, 350 would be like the best one, because if you get to the 400 again, which is like when you calcine the material, if you go further, then instead of having this porous structure, you get a spinel, which is a crystal salt. So that doesn't have the characteristics we need. So as long as you do the desorption about between 300 and 400, you're kind of on a safe range to do it.
Adsorption or desorption?
Desorption. So the adsorption can be done, from, I guess, from 0 to 250. So most of the studies have shown it has good results between 30 and 60, but some of them have shown that it is possible to do it at very, like 200, which is much more higher. And it's actually better in contrast with other solvents when it's done at higher temperatures. What I mean is that other adsorbents at lower temperatures have a better performance, but when it comes to increasing temperature, then they do not work anymore, but hydrotalcite still does the job.
Okay.
What's the water resistance of these? Do they pick up water?
Yes, they do, but it's actually interesting. They have this memory effect. So once you have calcined the structure, it doesn't have the layers structure anymore, and it's amorphous metal oxides. So when the water molecules get into contact, it actually reconstructs the layers, which is actually good. And some studies have shown that if there's about 10% of water in the flue gases, then the adsorption capacity increases a little bit. So it's, well, I found it quite interesting. Of course, if you increase much more the water, then it gets stuck with all the water and there's not so much carbon capture, but it's still interesting that even if you don't get away the water, it will capture CO2.
Yeah, I mean, particularly if it's hot flue gas, you won't be able to get rid of the moisture that's in it.
Yeah. Yeah, well, that's another reason why we're trying with this material, because it looked as if, well, if it can work at higher temperatures, it can work with water. It is very sensitive to the sulfur oxides, but we're working in a case basis of natural gas-fired power plant, so we're trying to simplify things for us for the moment. But yeah, it's good.
You have to watch out, even with natural gas power plants, because the stuff that's put in so that you can smell the natural gas contains sulfur as well, small amounts. So for some purposes, they have to take that out before you can use it.
Yeah.
Interesting.
Thank you.
Sorry, I have one question. No, sorry, two questions. It's the layer structure, yes, and do you know where the chemical reaction takes place in cation layer or ionic layer?
So as I mentioned, when you do the calcination of the material, it stops having these layered layer structure, sorry. So when the material, maybe this is too, yeah, maybe not the best image to show that, but okay, so when you have the material activated and it has this amorphous structure, most of the CO2 gets stuck into the part in which you have the aluminum with magnesium, because there is a change in the charge around the atoms. So the CO2 is more attracted to these active sites, are called, rather than like the whole structure. And also when you calcine it, the anions, which are water and carbonates, actually, well, the water evaporates and the carbonates are decomposed in CO2, ironically. But it can capture more CO2 than the one that you generate when you calcine it. So yeah, I guess if this structure was kind of preserved, then it would be around these changes. So green being the magnesium and orange being aluminum, then if everything is crumbled up, but this would be the site, the active site.
Yes, and my second question is also related somehow to this question. Yeah, because we use the charge transfer. We use I don't know, metal species for charge transfer the structure. And is that able to simulate other, because you consider the surface area in your simulation, is that able to consider other factors, like, I don't know, like how?
Yeah, well,
yeah.
Part of the reason why we chose the ReaxFF method to simulate this, well, there are other ways to do molecular simulation, but this one specifically can deal with the creation and disappearance of chemical bonds, which would reflect the chemical sorption. And these would also help us to I lost the train. Can you repeat the question, because I think I was diverging?
I'm just wondering if we can consider other factors.
Yeah. Okay.
Surface area. Yeah.
Yeah. Thank you. So with this capability of doing this chemical bonding formation, you can actually change temperature and pressure at which you're doing the simulation. So you can play around with which is like the optimum absorption temperature. Well, yeah. That will be for the ground canonical, but when you're calcining the material, you can vary how much you heat it up, and you can contrast that with the surface area at the different temperatures that we can find in literature. And also for the absorption capacity studies, you can vary the pressure and the temperature. So that's one of the reasons why we wanted to do this, because we want to have those insights passed on to the process simulation, because for now there are no studies at larger scale. So if we could manage to say, okay, we have found that at this pressure and temperature you have the highest capture capacity, then we would try to do that simulation on the process scale.
Yeah. Okay, thank you very much.
Thank you very much for that, Phoebe. We are going to move on to our next speaker, who is James Hendry. James is a research associate in chemical engineering at Newcastle University, working on using rotating packed beds for amine-based carbon capture. James will discuss progress in pilot-scale rotating packed bed carbon capture plants. Over to you, James.
Can you hear me, see me all right?
We can hear you and we can see your screen. Yes, thank you.
Yeah, are you looking at the poster I've got?
Yeah.
It's disappeared. Zoom. At Newcastle University, we're testing amine-based carbon capture processes in pilot-scale demonstration units. So we've got units that will do both the absorption and the regeneration step, and both of these machines are using rotating packed beds to intensify the carbon capture process. So the RPBs exploit a centrifugal field to dramatically improve the mass transfer in comparison to a conventional column. This substantially reduces the size of the equipment, and that's the main motivation, is to reduce the size of carbon capture plants required for power production in industrial processes, and therefore reduce the capital cost. We've also got additional benefits. They have a reduced response time, so that could make them more useful for load following power plants and transient operation. They've also got a lower solvent inventory and a bit more flexibility on the types of solvent you can use. So we have experience partnering with universities in collaborations and company contracted research involving RPBs, and that's both are something we want to continue and develop in the future. And this poster is just going to cover our current progress in the area. So this pilot plant facility, these are the machines that we've got at Newcastle, and really they're designed for basically flexible operation and under realistic conditions. So this is the absorber. We've basically got flexibility in terms of how we can set it up. We can get it set up really quickly with a number of configurations depending on what we want to achieve, and practical gas liquid flow ratios, and a humidified gas stream, because the humidity also affects the mass transfer. This schematic is basically showing what they would look like on a full-scale process, but it's basically exactly the same as a conventional amine process, with the columns replaced. The RPB is, in the regenerator side, is basically intensifying both the heat and mass transfer by combining the reboiler and the stripping process into one unit. That's our first prototype in that area, but the machine works essentially. So these two flow diagrams are basically showing how we set up the experiment. And again, it's just a focus on realistic conditions for the inlets and flexibility in operation. So this shows the mass transfer results, and we were able to improve the mass transfer by working with Julius Montz in the last project, in the EU Horizon 2020 project, to improve the mass transfer by optimizing packing design. This graph basically shows, I don't know if I can zoom in, basically shows the results from the integrated stripper reboiler, to show that the dotted line shows the conventional process, and these dots underneath show the reduction in reboiler duty we were able to achieve. And then this is really the last point that I wanted to concentrate on and draw your focus on. We're also doing this Artemis project, which will install this 1.1 metre rotating pack bed on this Dushan Babcock site in Glasgow, and that's aiming to achieve 90% carbon capture, testing at a technology readiness level of 7, so that's demonstration in an operational environment. And that will involve, this is just the absorption unit at the moment, but we'll be installing absorption and regeneration RPB processes to install it as basically a functioning intensified carbon capture pilot plant that can operate continuously. So yeah, that's my post. That's my talk. My poster / talk.
Okay, thank you very much, James. Are there any questions for James? Not yet. James, I was wondering, regarding the rotation of the packed beds, where does the energy come for the movement?
So to drive them, there is an energy cost associated with the rotation. That's driven by, basically, there's a motor, and just an electric motor driving the RPB, and the main energy cost is because you've got a liquid that starts at rest as it's introduced, and then when it's got a velocity as it leaves the bed. So that's the main energy cost, because it's continuous and you can't really recover it. Although we have worked on some recovery with the reboiler, it's not going to be like that. Energy is basically lost. And it increases with the size of the bed, so that's a motivation for making the machines smaller, which we've got several avenues to work on there. But yeah, it's not significant. It's nothing like the steam demand, for example. You know, I think it's a couple of megawatts for a full-scale process.
Okay, thank you. We have a question in the chat. Phebe, would you like to ask your question? would you like me to summarise?
Yeah, sorry,
Yeah,
I
perfect.
turned off the
Thank you.
microphones
No,
too. So yeah, I was just curious about how big is the difference by using a rotating bed in comparison with a fixed bed?
So in terms of size reduction?
In terms of the capture, well, yeah, like how much does it affect the capture capacity of the whole unit, and also does the energy that you need to put into the rotating bed is worth this increase or decrease of the capture capacity?
So it can reduce the size by about an order of magnitude, so about 10 times size reduction in the size of the column.
Great.
That does come with the additional operational costs because due to driving the motor, you know, due to driving the rotation.
So for example, like absorption wise, regardless of the equipment size, do you, well, I'm curious because I've seen that some adsorbents are better when they are in a fluidized bed because they have a better contact and mass transfer of the CO2 in the flue gases with the material. So I was just wondering if there's like a change with this.
We can use basically, well, one of the benefits we've got is that we can use more viscous solvents than would be practical when you're operating with a conventional column. So that gives us a lot more options in terms of the types of solvents we can use. Yeah, so that's something that we're working on. I can send you more details on what you're asking about the benefits versus disadvantages after the talk, if you like.
Yeah, that was interesting. Thank you.
Thank you. And John, would you like to ask your question?
Yeah, okay.
Thank you.
Just from the previous presentation we had, where it was challenging this 90% target that's often used, given this has quite a different footprint and capital cost, would you see it as something that you would run beyond 90% capture efficiency, or is 90% the optimum for how much you have to spend to get the carbon back?
That's a great question, but I'm not really sure. I'm not really sure because, I'm not really sure how it would work out. But basically, with this, we've gone for 90% carbon capture here, just because that's the standards that most people. But I can't really say if the RPB would be better or worse than the conventional technology for going to 98% capture at the moment. But it's definitely something I'd be interested in seeing. You know, I'm definitely convinced by Dr. Brandl's arguments for net zero and 100%. But there's definitely practical hurdles to cross for that.
Hi James, this is Patrick. If you don't mind adding my 2 pence to this. So the reason why a solvent process is so bad off is at the top of the absorber, you've got a very small driving force of the CO2 into your solvent. And with the rotating packed beds, because of the the centrifugal force, you can increase this driving force / mass transfer that is very slow at the top of my absorber. So I would expect the intensity of this cost increase that I'm seeing to be less with a rotating packed bed. So I would assume that you can go higher at a lower cost. The issue that I see is, and I have no clue, is it even possible to make it a bit wider in diameter with the centrifugal forces? So that's more a mechanical issue than a thermodynamics issue from my viewpoint. And then James, just a quick question, if you don't mind. When you say you can go to more viscous solvents, I was wondering, can you throw in stuff like ionic liquids, which is like 250 millipascal seconds?
Yeah, there's published work on ionic liquids and RPBs. I think there's like one paper from, but basically the paper is just like, you put ionic liquids in an RPB, here's a result. You know, it doesn't really say very much about from what I've, you know. So yeah, I'd definitely be interested in you know, we've been thinking about doing that, but yeah, I don't know. I don't know.
Well, maybe, so my issue with ionic liquids, they're more physical solvents. So I would throw some water lean, BOL, some type of water lean bioorganic liquid, the stuff that PNNL uses in there, because they've got high viscosity around 150 millipascal seconds, and then the slow heat transfer, the slow mass transfer because of viscosity limits them. And once you have the centrifugal force, you could speed it up. So that would be huge. I would be very interested in that.
Okay, thank you very much. Are there any more questions finally for James?
Just one short question. Okay, go on, John. Sorry.
Oh, well, just very quickly, corrosion. Have you looked at corrosion in these concentrated amine solutions? It seems to go up fairly rapidly.
Corrosion rates and things, not really. I know the material we use in the machine is compatible with the amines.
Yeah, even with stainless. I mean, we've seen that practically at 40% MEA, which is the highest concentration we've used in a conventional absorber.
Is that because of its corrosion?
I don't know. It just seems to react a lot quicker with stainless steel. That's all. Under those conditions, you know, as you increase the concentration.
Okay, I wasn't aware. I mean, I knew it would be different, but I wasn't aware that it would. Yeah, I'll look into that.
Yeah, well, it's certainly, you know, people in the conventional side of things think it's a problem going to concentrated amines for that reason. Also for heat transfer, as the viscosity goes up, you know, the cross-flow heat exchanger is that much more difficult.
Thank you. And was there one more final question?
Yes, just regarding the selectivity and how is the CO2 concentration, because you use mixed air?
The selectivity?
Yeah. Does it affect on the procedure because you use a mixed air, and how's the CO2 concentration should be? Or is that this procedure has a high selectivity or not?
Yeah, it would be high selectivity because the amine basically reacts with CO2. So you form an amine carbonate that, so it's a bit like the reaction between an alkali and the acidic CO2. So you basically just absorb CO2 and then desorb it in the regenerator.
Okay. Thanks.
Okay, I think we've. Thank you, James. That's the end of our last speakers for today. And now we just.
So yeah, I just want to say thank you to everyone for presenting today.
Yeah.
It's great to hear all the different kind of research that's going on and hear from hear from everyone. And an especially big thanks to both Patrick and Louise for chairing today's session as well. So yeah, thank you to both of you, and thank you to everyone for attending. We've got our next poster session next week. So we've got another poster session on Tuesday, the same time next week, as well as a drop-in webinar session with 2 presenters tomorrow as well. So yeah, I hope to see lots of you tomorrow and next week as well. So thank you, everyone.
Thanks, Carries, and thank you to all our speakers. Thank you.
Thank you and bye.
Thanks, bye-bye.